Light is fast, the fastest thing in the universe. Yet when you look at the stars, you're looking at the past. That star overhead, its light has been traveling for years, maybe decades, sometimes centuries. The star itself might have already died, collapsed, exploded into a supernova. Yet there it is, still shining in your sky. Why does this happen? If light is so fast, crossing 300,000 kilometers every single second, why does it take so long to reach us? And here's the deeper question. What does this delay mean for everything else you see? For the sun? For the person across from you? For the present moment itself? Welcome to Sleep Knowledge. Tonight, we're going to explore the delayed universe not as a glitch, but as the fundamental architecture of reality. And along the way, we'll discover why light's finite speed is the universe's way of keeping past, present, and future from collapsing into each other. We'll explore how light's speed creates the world you experience, not to disturb your sense of the present moment, but to show you why the present moment has the shape it does. Why you live in a universe where cause must precede effect, and why that delay isn't a limitation, it's what makes reality coherent. Let's begin with something that feels simple. Light moves. It travels from one place to another. A photon leaves the surface of a star, crosses the emptiness of space, and eventually enters your eye. That journey takes time. And the farther the star, the longer the journey. This seems straightforward. Distance divided by speed equals time. The same arithmetic that works for cars on highways works for light crossing the cosmos. But there's something strange hidden in that arithmetic. Light doesn't just move fast, it moves at a very specific speed, always, everywhere, no matter who's watching or how they're moving. 299,792,458 meters per second. Not approximately, exactly. By definition. That precision might sound like a technicality, but it's not. It's a clue. A hint that light's speed isn't just another number to measure, it's woven into the structure of reality itself. For most of human history, no one knew light had a speed at all. It seemed instantaneous. You open your eyes, and the world is simply there. No delay, no travel time, just immediate presence. Galileo tried to test this in the early 1600s. He and an assistant stood on distant hilltops with covered lanterns. Galileo would uncover his lantern, and the assistant was supposed to uncover his the moment he saw Galileo's light. By measuring the time between Galileo's action and seeing his assistant's response, he hoped to calculate how long light took to cross the distance. It didn't work. Human reaction time was far too slow. The distance is far too short. If light had a speed, it was faster than his experiment could detect. The first real evidence came from an unexpected place, the moons of Jupiter. In 1676, Danish astronomer Ole Rømer was carefully tracking Io, one of Jupiter's 4 large moons discovered by Galileo. Io orbits Jupiter every 42.5 hours, regularly disappearing behind the planet and re-emerging on the other side. Rømer noticed something odd. When Earth was moving toward Jupiter in its orbit, Io's eclipses happened earlier than predicted. When Earth was moving away from Jupiter, the eclipses happened later. The pattern was consistent, predictable. The difference added up to about 22 minutes over the course of Earth's year. Rømer realized what this meant. Light from Jupiter wasn't arriving instantly. It was traveling across space, taking time to reach Earth. And as Earth's distance from Jupiter changed, that travel time changed too. He calculated a rough speed, about 220,000 kilometers per second. Not perfect, but close enough to prove the fundamental point. Light has a speed. Over the next 2 centuries, scientists refined the measurement. They built better instruments, controlled conditions more carefully, reduced sources of error. In 1849, French physicist Hippolyte Fizeau used a rotating toothed wheel to chop a beam of light into pulses. He sent the light to a mirror 8 kilometers away and measured how fast the wheel needed to spin for the returning light to pass through the next gap between teeth. His result? 315,000 kilometers per second. Closer. Léon Foucault refined the technique in 1862, using rotating mirrors instead of toothed wheels. His measurement, 298,000 kilometers per second. Closer still. By the early 20th century, the value had been pinned down with extraordinary precision, and something strange had become clear. Light's speed didn't just seem constant, it was constant. Perfectly, stubbornly, impossibly constant. Here's where intuition starts to strain. In everyday experience, speeds add and subtract depending on your motion. Stand on a train platform and watch a train pass at 100 kilometers per hour. Someone on the train throws a ball forward at 20 kilometers per hour. From your perspective on the platform, the ball is moving at 120 kilometers per hour. That's how speeds work. They combine. They're relative to the observer. But light doesn't do this. Shine a flashlight while standing still. Light leaves the flashlight at 299,792,458 meters per second. Now imagine you're on a spaceship moving at half the speed of light, something impossible for humans, but useful as a thought experiment. You shine the same flashlight forward. Intuition says the light should now be moving faster, half the speed of light from your motion, plus the full speed of light from the flashlight. It should add up to 1.5 times light speed. But it doesn't. The light still leaves the flashlight at exactly 299,792,458 meters per second. Not faster, not slower. The same speed. This feels wrong. Not just surprising, fundamentally incompatible with how motion should work. And yet, experiment after experiment confirms it. By the late 1800s, this strange constancy had become a real problem for physics. At the time, scientists believed light was a wave traveling through a medium called the luminiferous ether, an invisible substance filling all of space. Waves need something to wave through. Water waves travel through water, sound waves travel through air. Light waves, scientists reasoned, must travel through ether. If that were true, then Earth's motion through the ether should create a detectable ether wind. Think of it like this. If you're in a boat, moving across a lake, you feel wind even on a calm day, because you're moving through the air. Similarly, Earth moving through the ether should create a measurable difference in light's speed depending on direction. In 1887, physicists Albert Michelson and Edward Morley designed an extraordinarily sensitive experiment to detect this ether wind. They split a beam of light and sent it along 2 perpendicular paths, then recombined the beams. If Earth was moving through the ether, light traveling in the direction of Earth's motion should move slightly slower than light traveling perpendicular to it, like swimming upstream versus across a river. The apparatus was sensitive enough to detect even tiny differences, but when they performed the experiment, they found nothing. No ether wind, no variation in light speed. No matter which direction they pointed their apparatus, light traveled at the same speed. They repeated the experiment, refined it, tried different orientations, different times of year. Same result. Light speed was the same in every direction. This created a crisis in physics. Either the ether existed but somehow didn't affect light speed, which made no sense, or the ether didn't exist at all, which left light with no medium to travel through. Worse, if light speed was truly constant for all observers, something deeper had to be wrong with the understanding of motion, space, and time. Scientists proposed various explanations. Maybe the ether was dragged along by Earth's motion. Maybe the apparatus contracted in the direction of motion, perfectly cancelling the effect. Maybe there was some other mechanism no one had thought of yet. But these explanations felt increasingly forced. Patching one problem created others. The tension built for nearly 2 decades. And then, in 1905, a 26-year-old patent clerk named Albert Einstein proposed something radical. Einstein didn't try to explain why light's speed was constant. He accepted it as a fundamental fact and asked, what if the universe actually works this way? What if light speed is the same for every observer, not because of some complicated mechanism, but because that's simply how reality is structured? If that were true, then something else had to give. And what gives, what bends, what changes, is time and space themselves. This is where the strangeness deepens. Imagine you're standing on a train platform. A train passes by at high speed. Someone on the train shines a flashlight forward. From your perspective on the platform, the light from the flashlight should be moving faster than normal, the train's speed plus light speed. But it's not. You measure the light moving at exactly 299,792,458 meters per second. Meanwhile, the person on the train also measures the light from their flashlight. From their perspective, they're standing still and the light is moving away from them. They also measure 299,792,458 meters per second. Both measurements are correct. Both observers are right. But how can that be? The only way for both observers to measure the same speed is if they're measuring distance and time differently. Not because their instruments are faulty, not because one of them is wrong, because distance and time actually are different for them. This is time dilation. When you move relative to something else, time passes differently for you than for someone who's stationary. Not metaphorically, actually. Clocks moving at high speeds tick more slowly than stationary clocks. Not because they're broken, because time itself is passing more slowly. The effect is real, measurable, confirmed by countless experiments. It's also tiny at everyday speeds. A passenger on a commercial airplane ages about 100 nanoseconds, less than someone on the ground during a long flight, unnoticeable in daily life, but absolutely real. At speeds closer to light speed, the effect becomes dramatic. Travel at 90% the speed of light, and time slows to about half its normal rate. Travel at 99% the speed of light, and time slows to 1/7. Travel at 99.99% the speed of light, and time nearly stops. But here's what's crucial. From your perspective, nothing feels different. Your heartbeat is normal, your thoughts move at their usual pace. Time always feels like time to the person experiencing it. It's only when you compare your clock to someone else's, someone who hasn't been moving at those speeds, that the difference becomes visible. This isn't just theory. In the 1970s, physicists Joseph Hafele and Richard Keating performed a now famous experiment. They took 4 atomic clocks, some of the most precise timekeeping devices ever built, and flew them around the world on commercial airliners. 2 clocks flew eastward. 2 flew westward. When they returned and compared the travelling clocks to identical clocks that had stayed on the ground, the travelling clocks had fallen behind. Not by much, just a few hundred nanoseconds. But the difference was exactly what Einstein's equations predicted. Time had actually passed more slowly for the moving clocks. Another confirmation comes from particle accelerators. At facilities like CERN in Switzerland, physicists accelerate subatomic particles to speeds approaching light speed. One common particle used in these experiments is the muon, a heavy cousin of the electron. Muons are unstable. They decay quickly on average. They last about 2.2 microseconds before breaking apart. At high speeds, muons should travel only about 660 meters before decaying. That's just how much distance they can cover in 2.2 microseconds, even moving close to light speed. But in particle accelerators, muons routinely travel several kilometers before decaying. Why? Because, from the perspective of a stationary observer, time is passing more slowly for the moving muon. Its internal clock, the process that governs its decay, is running in slow motion. The muon thinks only 2.2 microseconds have passed, but to the observer, far more time has elapsed. This isn't a quirk of muons, it's a consequence of how time works at high speeds, and it's been confirmed thousands of times in laboratories around the world. But time dilation isn't the only consequence of light's constant speed. Space changes too. This is called length contraction. An object moving at high speed becomes shorter in the direction of its motion, not because it's physically compressed, but because space itself is different for that object. From the object's perspective, it hasn't changed at all. It's the stationary world that looks compressed. This reciprocal strangeness is one of relativity's most disorienting features. You see a spaceship moving past you at 90% of light speed. To you, the spaceship looks squashed shorter than it should be. But to the people on the spaceship, they're perfectly normal. It's you and the entire universe around you that looks compressed. Both perspectives are equally valid. Neither is wrong. Space and time are simply not absolute. They depend on motion. So let's take stock of where we are. Light travels at a constant speed always, for every observer. This constancy forces time to be relative. Moving clocks tick more slowly than stationary ones. It also forces space to be relative. Moving objects become shorter in their direction of motion. These aren't just mathematical tricks. They're real, physical effects, confirmed by experiments. And they all stem from one simple fact. Light speed doesn't change. But here's where it gets even stranger. Why should light speed be constant? What makes it so special? The answer has to do with what light actually is, and with what the speed of light actually represents. Light is an electromagnetic wave. This wasn't always obvious. For centuries, scientists debated whether light was a particle or a wave. Newton thought it was made of tiny corpuscles. Others argued it behaved like ripples in a pond. By the mid-1800s, experiments had clearly shown wave behavior. Light could diffract around corners. It could interfere with itself, creating patterns of bright and dark bands. Waves did that. Particles didn't. But what was waving? In the 1860s, Scottish physicist James Clerk Maxwell worked out a set of equations describing electricity and magnetism. These equations showed that electric and magnetic fields could propagate through space as waves. And when Maxwell calculated how fast these electromagnetic waves should travel, he got a very specific number: 299,792,458 meters per second. The speed of light. This wasn't a coincidence. Light was an electromagnetic wave, a ripple in electric and magnetic fields, traveling through space at a speed determined by the fundamental properties of those fields. Maxwell's equations didn't just describe light, they predicted it. But here's the crucial part. Maxwell's equations don't care who's measuring. They don't include a term for the observer's motion. They simply say, electromagnetic waves travel at this speed, period. Not this speed relative to the ether. Not this speed depending on your reference frame. Just this speed, always. This is why the Michelson-Morley experiment found no ether wind. The equations didn't predict one. Light speed was built into the structure of electromagnetism itself, independent of any medium. The universe wasn't being difficult, it was being consistent. This connects to something even deeper. The speed of light isn't really about light. It's about causality. Causality is the principle that cause precedes effect. You flip a switch, then the light turns on. You throw a ball, then it flies through the air. Events happen in order, and that order matters. But order depends on timing, and timing depends on how fast information can travel. Think about it this way. If you could send information faster than light, you could create situations where cause and effect become scrambled. From one perspective, event A happens first, then event B. From another perspective, moving at a different speed, event B happens first, then event A. If event A causes event B, this creates a logical contradiction. The effect would precede its own cause. Time travel paradoxes would become commonplace. The universe avoids this by enforcing a speed limit. No information, no cause, no influence, no signal can travel faster than light. This keeps causality intact. It prevents contradictions. It maintains logical consistency. Light happens to travel at this speed because light is massless. And massless things with no rest, mass at all, must travel at the maximum speed allowed by the universe. They can't travel slower. They have no mass to slow them down. They can't travel faster. There is no faster. So they move at exactly c, the speed of causality, the speed of light. Other massless particles do the same. Gluons, which carry the strong nuclear force, travel at light speed. Gravitons, if they exist, would travel at light speed too. The speed isn't special because light is special. Light is revealing something fundamental about how the universe is structured. This brings us to one of the most profound consequences of light's finite speed: the delayed universe. Everything you see is in the past. Not metaphorically, literally. Every photon that enters your eye took time to get there, and that travel time means you're seeing things as they were, not as they are. The delay is tiny for nearby objects. Light from across a room takes about 10 nanoseconds to reach you. Imperceptible, functionally instantaneous. But scale up and the delays become noticeable. The sun you see in the sky is 8 minutes old. If the sun suddenly vanished, impossible, but useful to imagine, you wouldn't know for 8 minutes. For 8 minutes, you'd continue seeing sunlight, warmth, a bright star in the sky. Then, all at once, darkness. Not because the darkness travelled to you, but because the last light from the sun finally arrived. The moon is about 1.3 seconds away. When astronauts on the moon spoke to Mission Control in Houston, their words took 1.3 seconds to travel there via radio signals, which are also electromagnetic waves, travelling at light speed. Mission Control's reply took another 1.3 seconds to travel back. Every conversation had a built-in 2.6-second delay. Not because of technology limitations, because of the speed of light. The universe itself enforces that delay. Mars is farther. Depending on where Earth and Mars are in their orbits, the distance varies between about 55 million and 400 million kilometers. At closest approach, light takes about 3 minutes to travel from Mars to Earth. At farthest separation, over 22 minutes. Rovers on Mars can't be controlled in real time. Engineers send a command, then wait. Minutes pass. The rover receives the signal, executes the command, sends confirmation back. More minutes pass. By the time confirmation arrives, the rover has already moved on. This isn't a technical challenge to overcome. It's a fundamental constraint. The distance is real, light speed is finite, and delay is unavoidable. The nearest star beyond the Sun is Proxima Centauri, about 4.24 light-years away. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. Proxima Centauri's light takes 4.24 years to reach Earth. When you look at Proxima Centauri, you're seeing it as it was over 4 years ago. If something happened there today, a flare, a planet forming, the star exploding, you wouldn't see it for another 4 years. The event is real. It's happening. But from your perspective, it hasn't happened yet. The delay creates a strange kind of separation. Not just distance, but temporal distance. You and Proxima Centauri exist in the same present moment, yet you can't see each other's present, only each other's past. Most stars visible to the naked eye are tens or hundreds of light years away. Betelgeuse, the red supergiant in the constellation Orion, is about 650 light years away. The light you see tonight left Betelgeuse around the year 1375 before the printing press, before Columbus, during the late Middle Ages. Betelgeuse is expected to go supernova sometime in the next 100,000 years. It might have already exploded. The light from that explosion might be crossing space right now, halfway to Earth. But you won't know until the light arrives. When it does, it will be spectacular, bright enough to see during the daytime, rivaling the full moon at night. But that brightness will be 650 years old, a message from the deep past, finally delivered. Galaxies push this even further. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 2.5 million light-years away. When you see Andromeda, a faint smudge of light visible on dark nights, you're seeing it as it was 2.5 million years ago. Before modern humans existed. Before Homo sapiens evolved. The light crossing space right now left Andromeda when our ancestors were still Australopithecus, walking upright but not yet using tools. By the time that light reaches Earth, passes through the atmosphere, and enters your eye, millions of years have passed. But the photon itself, from its own perspective, if it had one, experienced no time at all. This is one of the strangest consequences of relativity. At light speed, time stops. A photon emitted from a distant galaxy travels for billions of years from the perspective of a stationary observer. But from the photon's own frame of reference, the journey is instantaneous. Emission and absorption happen in the same moment. No time passes. The photon doesn't experience the journey at all. This isn't a metaphor. It's a direct consequence of time dilation. As you approach light speed, time slows. At exactly light speed, which only massless particles can achieve, time stops completely. So light crosses the universe instantly from its own perspective, yet takes billions of years from ours. Both perspectives are real. Neither is wrong. They're just different views of the same journey. This delayed universe isn't a limitation to work around. It's the structure of reality. The speed of light creates the past, present, and future by determining what can influence what and when. Events that are far enough apart in space can't immediately affect each other. They're separated by light travel time. This separation creates a kind of buffer, a region of space-time where events unfold independently before their influences can reach each other. This buffer is what allows causality to be consistent. Without it, the order of events would depend on who's watching. Cause and effect would become scrambled. The universe would lose logical coherence. So the delayed universe, the fact that everything you see is already in the past, isn't a bug. It's a feature. It's what makes the present moment possible at all. But there's another consequence of light's special speed. One that feels even more restrictive. Nothing with mass can ever reach light speed. Not because we lack powerful enough engines, not because we haven't figured out the right technology, because the universe won't allow it. Here's why. As an object with mass accelerates, it gains energy. That part is intuitive. You push harder, the object moves faster, energy increases. But in relativity, something strange happens to that energy. It doesn't all go into speed. Some of it goes into increasing the object's mass. Not its rest mass, the mass it has when standing still. That doesn't change. But its relativistic mass, the mass it effectively has when moving at high speeds, increases. The faster you go, the more massive you become. At 90% of light speed, your mass is about 2-3 times your rest mass. At 99% of light speed, your mass is about 7 times your rest mass. At 99.99% of light speed, your mass is over 70 times your rest mass. And as your mass increases, it takes more and more energy to accelerate you further. Each tiny increase in speed requires exponentially more energy. By the time you approach light speed, your mass approaches infinity, and the energy required to push you faster also approaches infinity. Infinite energy is not available, not in this universe, not anywhere. So you can never quite reach light speed. You can get closer and closer. 99.9%, 99.99%, 99.99%, 99%, but never 100%. The universe has a built-in brake system. The closer you get to light speed, the harder it pushes back. This isn't theoretical speculation. Particle accelerators demonstrate this every day. At CERN, protons are accelerated to 99.9999991% of light speed. That's within a hair's breadth, but not quite there. To accelerate them even a tiny bit faster would require enormous additional energy. Energy that increases exponentially with each fraction of a percent gained. The particles get heavier instead of faster. Their momentum continues increasing. Their energy continues increasing. But their speed asymptotically approaches light speed without ever reaching it. This is exactly what Einstein's equations predict, and exactly what experiments confirm. So why can light reach light speed if nothing else can? Because light has no mass. More precisely, photons have no rest mass. They're never at rest. They're always moving at light speed. Without mass, there's no resistance to acceleration, no increasing relativistic mass, no exponentially growing energy requirement. Massless particles don't gradually speed up to light speed. They're created already moving at light speed, and they never slow down. This is true for all massless particles. Photons, gluons, gravitons, if they exist. They all travel at c, not because they're trying to, because they can't do anything else. In a way, the speed of light isn't really a speed limit. It's the speed that massless things naturally have. Everything else, everything with mass moves slower. This connects to one of the most famous equations in physics. E equals mc squared. Energy equals mass times the speed of light squared. This equation comes directly from relativity. It shows that mass and energy are equivalent two forms of the same thing. The c squared is the conversion factor. It tells you how much energy is locked up in a given amount of mass. And because c is such a large number, and c squared is astronomically larger, even tiny amounts of mass contain enormous energy. 1 kilogram of matter, if converted entirely to energy, would release about 90 quadrillion joules, enough to power a city for weeks. Nuclear reactions tap into a tiny fraction of this energy. The sun fuses hydrogen into helium, converting about 0.7% of the hydrogen's mass into energy. That 0.7% is what powers the sun's light for billions of years. The speed of light appears in this equation not because light is involved, but because c is the fundamental conversion factor between mass and energy in spacetime. It's another hint that light speed isn't about light. It's about the geometry of the universe. This geometry is what Einstein called spacetime. Before relativity, space and time were considered separate. Space was the three-dimensional stage where events happened. Time was the universal clock ticking forward, the same for everyone. Relativity showed that this separation is an illusion. Space and time are connected. They form a unified four-dimensional structure called spacetime. Events don't just happen at a location in space. They happen at a location in spacetime, a specific place and a specific time. And the speed of light is the conversion factor between space and time. It tells you how much time corresponds to how much space. Move through space, and you move through time differently. The faster you move through space, the slower you move through time. And at light speed, all your motion is through space, none through time. This is why photons don't experience time. They're moving through space at the maximum rate, which means they're not moving through time at all. There's a useful way to think about this. Everything moves through space-time at the speed of light. Always. When you're sitting still, not moving through space, all your motion is through time. Time passes normally. When you start moving through space, some of your motion shifts from time into space. The faster you move through space, the slower you move through time. Your total speed through space-time never changes. It's always c. What changes is how that motion is divided between space and time. This is why time dilation happens. Not because moving clocks are somehow broken or affected by their motion, but because motion through space reduces motion through time. It's a consequence of the geometry of space-time itself. And that geometry is determined by the speed of light. The value of c, 299,792,458 meters per second, sets the scale. It determines how much space corresponds to how much time. It sets the exchange rate, so to speak. Why this particular value? We don't know. It's one of the fundamental constants of nature. We measure it, but we can't derive it from anything more fundamental. It's just part of how the universe is, like the strength of gravity, or the mass of an electron, or Planck's constant. These numbers define the universe we live in. Change them, and you'd get a different universe. Perhaps one where stars couldn't form, or where atoms couldn't exist, or where chemistry couldn't happen. But in this universe, c has the value it has, and that value shapes everything. So let's return to where we started. Light is fast. Fast enough to circle the Earth 7.5 times in 1 second. Fast enough to reach the moon in a heartbeat. Yet when you look at the stars, you're looking at the past. Because even at that speed, the distances are vast. Vast enough that light takes years, centuries, even billions of years to cross them. This isn't a failing of light. It's the structure of the universe. Light's finite speed creates the delayed universe you live in. It enforces causality. It prevents contradictions. It maintains the logical order of events. It transforms space and time from separate, absolute things into a unified relative structure. And it does all this not because light is special, but because c, the speed of light, is the fundamental constant that connects space and time. The speed of causality, the maximum rate at which reality can update itself. But there's more to explore. Because light's speed doesn't just affect how fast things can travel. It affects what can happen. What events can influence each other? What futures are possible? This is where space-time becomes not just a mathematical abstraction, but a physical reality with structure and shape. Imagine an event. Not a grand cosmic event, just something simple. A light bulb turns on. That event happens at a specific location in space and at a specific moment in time, is less than #0. 5 is greater than. It exists at one point in space-time. Now ask, what other events can this event influence? The answer depends on light speed. Light from the bulb travels outward in all directions at c. 1 second later, that light has reached everything within 1 light second, about 300,000 kilometers. Anything within that distance could have seen the light, could have been affected by it. Anything beyond that distance cannot have been affected yet. The light hasn't reached it. 2 seconds later, the light has traveled twice as far. 3 seconds later, 3 times as far. The expanding sphere of light defines a boundary. Inside that boundary, events that could have been affected. Outside that boundary, events that couldn't have been affected yet. This boundary is called a light cone. The light cone has 2 parts. The future light cone includes all events that this event could possibly influence. Any event within the future light cone can receive light, particles, or information from the original event. Cause can reach effect. The past light cone includes all events that could have influenced this event. Any event within the past light cone could have sent light, particles, or information that arrived in time. Effect traces back to cause. Everything outside both light cones is space-like, separated from the original event. These are events that are too far away in space and too close in time for light to connect them. They cannot influence each other. Not yet, anyway. This structure, light cones defining what can influence what is, how causality works in relativity. It's not a vague philosophical principle. It's a geometric fact about spacetime. Here's where it gets strange. For events inside your future light cone, all observers agree on the order. This event happened first, then that event. Cause, then effect. But for events outside your light cone, events that are space-like separated, different observers can disagree about the order. From one observer's perspective, event A happens first. From another observer's perspective, moving at a different speed, event B happens first. Both observers are right. There's no absolute order for space-like separated events. This sounds like it should create problems. If the order of events depends on who's watching, doesn't that break causality? No, because space-like separated events can't influence each other. If A can't affect B and B can't affect A, then it doesn't matter which one happens first. The order is ambiguous, but harmlessly so. Causality is preserved because the light cone structure guarantees that if A causes B, all observers agree on that order. The speed of light enforces this. It's the boundary between what can influence you and what can't. This has practical consequences. Simultaneity, the idea that 2 events happen at the same time, is relative. Not just hard to determine, actually relative. Imagine 2 events happening on opposite sides of the Earth. From your perspective, they happen simultaneously. But someone moving at high speed relative to you, say, in a spaceship passing by, would see one event happen before the other. Not because their clock is wrong. Not because light takes different amounts of time to reach them. Because simultaneity itself is relative. There's no universal now. No moment that is the present for everyone, everywhere. Your now includes events that are simultaneous from your perspective. Someone else's now includes a different set of simultaneous events. The present moment is observer-dependent. Einstein illustrated this with a thought experiment. Imagine you're standing on a train platform. A train passes by at high speed. Lightning strikes at both ends of the train, simultaneously from your perspective. You're standing exactly halfway between the 2 strikes. Light from both strikes reaches you at the same instant. You conclude the strikes happened simultaneously. But someone on the train standing in the middle of the train sees things differently. The train is moving toward one strike and away from the other. From their perspective, light from the front strike arrives first. Light from the rear strike arrives later. They conclude the front strike happened first, then the rear strike. Both of you are right. The strikes were simultaneous in your reference frame. They were not simultaneous in the train's reference frame. This isn't a trick of perception. Simultaneity is genuinely relative. Different frames of reference have different now moments. This shakes one of the deepest intuitions about time. The idea that there's a universal present, a moment that is now, for everyone feels fundamental. It's built into language, into thought, into the structure of human experience. But relativity says it's not true. The present moment is local, personal, observer-dependent. Someone on Earth and someone on a distant planet don't share the same now. Their present moments are different slices through spacetime. This doesn't make reality inconsistent. It makes it richer, more complex, less tied to human intuition. The universe doesn't care what feels obvious. It operates according to its own logic, and that logic is internally consistent, even if it's counterintuitive. So what does this mean for the experience of the present? You experience time as flowing. Moments pass. The future becomes the present, then recedes into the past. This feels real, and, in a sense, it is. But it's not the whole story. From a relativistic perspective, all moments exist equally. Past, present, and future are all part of spacetime, a four-dimensional structure where every event has a definite location in space and time. This is sometimes called the block universe. The idea is that spacetime is like a solid block containing all of history and all of the future. Your experience of now is like a slice through that block. The slice moves, or seems to move, giving you the sensation of time flowing. But all the slices exist. They're all equally real. This is philosophically unsettling. It suggests that the future already exists, just as the past still exists, and free will might be an illusion. But it's important to be careful here. Relativity doesn't prove the block universe is the correct interpretation. It shows that spacetime has a four-dimensional structure and that simultaneity is relative. How to interpret that structure, whether the future exists in the same sense as the past, whether time truly flows or just seems to remains, open to debate. Physics describes how things behave. Philosophy interprets what that behavior means. And on questions like this, philosophy hasn't settled on one answer. What relativity does make clear is this: time is not what it seems. It's not a universal, absolute progression that everyone experiences the same way. It's flexible, relative, interwoven with space. And the speed of light is the thread that weaves them together. It sets the exchange rate between space and time. It defines what events can influence each other. It creates the structure of past, present, and future. Without light's finite speed, space-time would collapse into incoherence. Causality would fail. The universe would lose its logical structure. So when you look at the stars and see the past, you're not just observing a delay. You're seeing the fundamental architecture of reality. The delayed universe isn't a limitation to work around. It's the only way a causally consistent universe can exist. Light's speed creates that consistency, and in doing so, it creates the possibility of a coherent, ordered reality where cause precedes effect, where events unfold in sequence, and where time has meaning. But light's speed affects more than just causality and time. It also shapes how we observe the universe. Every telescope is a time machine. Not in the science fiction sense, you can't travel back and change the past. But in a literal sense, every photon that enters a telescope is a messenger from the past. The deeper into space you look, the farther back in time you see. The Hubble Space Telescope has captured images of galaxies over 13 billion light-years away. That light left those galaxies over 13 billion years ago. The universe itself is only about 13.8 billion years old, so that light shows galaxies as they were when the universe was young, less than 1 billion years old. Those galaxies don't look like that anymore. Billions of years have passed, stars have formed and died, galaxies have collided and merged. But from Earth's perspective, those events haven't happened yet. The light from those events is still on its way. It will arrive millions or billions of years in the future. By then, humanity might be gone. The Earth might be gone. But the light will still arrive, carrying information about events that happened eons ago. The James Webb Space Telescope pushes even deeper. It's designed to see the first galaxies that formed after the Big Bang galaxies, so distant, their light has been travelling for over 13.5 billion years. These are the earliest galaxies, the first stars igniting in the primordial darkness. We see them not as they are, but as they were when the universe was in its infancy. We're looking at cosmic history, ancient light finally arriving. There's a limit to how far we can see, not because telescopes aren't powerful enough, but because there's a horizon built into the structure of space-time. Before the universe was about 380,000 years old, it was too hot and dense for light to travel freely. Photons couldn't move far before being absorbed and re-emitted by charged particles. The universe was opaque. Then, as the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms. Suddenly, photons could travel unimpeded. The universe became transparent. The light from that moment, the moment the universe became transparent, is still traveling through space. It's called the cosmic microwave background, a faint glow filling the entire sky, visible in every direction. This light has been traveling for over 13.8 billion years. It's the oldest light we can see, the most ancient message the universe has sent. And it tells us what the universe looked like when it was just 380,000 years old. Hot, dense, nearly uniform, but with tiny variations, seeds that would eventually grow into galaxies. We can't see farther back than this. Not because the universe didn't exist before, then it did, but because light couldn't travel freely, there's no light from earlier times to observe. The cosmic microwave background is a kind of wall. Beyond it, the universe is invisible to light-based observations. This doesn't mean we know nothing about earlier times. Physics can extrapolate backward, using equations and observations to infer what conditions must have been like. But direct observation stops at the cosmic microwave background. Light's finite speed, combined with the universe's history, creates an observational horizon, a boundary we cannot see past. This horizon is moving. Every second, light from slightly farther away reaches us for the first time. The observable universe grows, not because new regions are being created, but because light from those regions is finally arriving. In a sense, the universe is revealing itself slowly. Each moment, a little more comes into view. But there are also regions we will never see, because the universe is expanding. And in some directions, it's expanding faster than light can travel toward us. Light from those regions will never reach us, not because light is too slow, but because the space between us and those regions is stretching faster than light can cross it. This creates a cosmological horizon, a boundary beyond which the universe is forever hidden from view. So the delayed universe has layers. Nearby objects show the recent past. Distant objects show the ancient past. The cosmic microwave background shows the moment the universe became transparent. And beyond that, nothing. Not because nothing is there, but because light cannot bring information from those times and places. The speed of light is finite, and that finitude creates boundaries. Boundaries in space, boundaries in time. Boundaries on what can be known. But light's finite speed isn't just an abstract cosmic principle. It affects everyday life in subtle but important ways. Consider GPS. The global positioning system relies on satellites orbiting Earth, each carrying precise atomic clocks. Your phone receives signals from multiple satellites, measures how long each signal took to arrive, and calculates your position based on those travel times. The signals are electromagnetic waves, radio waves, specifically traveling at the speed of light. The system works because light speed is constant and known. But here's the subtlety. The satellites are moving relative to you. They're also higher up in Earth's gravitational field. Both effects, motion and gravity, cause time to pass differently for the satellites than for you on the ground. Special relativity says moving clocks tick slower. The satellites are moving at about 14,000 kilometers per hour, so their clocks should run slower than clocks on the ground. This effect would cause the clocks to lose about 7 microseconds per day. General relativity says clocks in weaker gravitational fields tick faster. The satellites are higher up, where gravity is slightly weaker, so their clocks should run faster than clocks on the ground. This effect would cause the clocks to gain about 45 microseconds per day. The two effects partially cancel, but don't fully offset each other. Net result: satellite clocks run about 38 microseconds faster per day than ground clocks. That might not sound like much, but light travels about 300 meters in 1 microsecond. 38 microseconds means an error of over 11 kilometers. Without correcting for relativity, GPS would drift by kilometers every day. It would be useless for navigation. So GPS systems account for both special and general relativity. The satellite clocks are adjusted to tick at a slightly different rate, compensating for the relativistic effects. This adjustment happens continuously, in real time. Every position calculation you make with your phone depends on Einstein's equations being correct. Relativity isn't just theoretical. It's woven into the technology you use every day. Another place light speed becomes crucial: telecommunications. Fiber optic cables carry information as pulses of light. The internet, phone calls, video streams, all traveling at light speed through glass fibers. But even at that speed, distance creates delay. A signal traveling from New York to London about 5,500 kilometers as the cable runs takes about 28 milliseconds. Not long, but noticeable in certain applications. High-frequency trading in financial markets, for example, operates on microsecond timescales. Traders position their servers as close to stock exchanges as possible to minimize light travel delay. A few milliseconds, a few extra meters of cable can mean the difference between profit and loss. The speed of light becomes a competitive constraint. Information cannot travel faster. Geography matters, even in the digital age, because light speed is finite. That there's a phenomenon that seems to challenge this limit: quantum entanglement, one of the strangest predictions of quantum mechanics. When two particles are entangled, measuring one instantly affects the other, even if they're separated by vast distances. Change the state of one particle, and the other particle's state changes immediately, instantaneously, faster than light. At least, that's how it's often described. Einstein famously called this spooky action at a distance. He thought it revealed a flaw in quantum mechanics. Surely, he reasoned, information couldn't travel faster than light. Surely, there must be some hidden mechanism, some local explanation. But experiments have repeatedly confirmed entanglement is real. Measure one particle, and the other particle's state is instantly determined, no matter how far apart they are. So does this violate relativity? Does entanglement allow faster than light communication? No, and here's why. When you measure an entangled particle, you get a random result. You can't control what result you get. You can't choose to make your particle spin up or spin down. The measurement outcome is probabilistic. The other particle's measurement will be correlated with yours. If you get spin up, the other particle will get spin down, and vice versa. But you can't use this to send information, because the person measuring the other particle also gets a random result. They see spin up or spin down, seemingly at random. They have no way to know whether their result is correlated with yours unless you tell them using normal, slower-than-light communication. Only when you compare results later do you see the correlation, and that comparison requires sending information at or below light speed. So entanglement creates correlations instantaneously, but doesn't transmit information instantaneously. No messages, no signals, no data. Just correlations that can only be verified later, through normal communication. Relativity is safe. Causality is preserved. The speed of light remains the maximum speed for information. This is a subtle but crucial distinction. Entanglement shows that quantum mechanics has non-local features. Particles separated by vast distances can be connected in ways that seem to transcend space. But non-locality doesn't mean faster than light communication. It means correlations can exist across space without signals traveling through space. The universe is stranger than classical physics suggested. But it's not incoherent. It still respects causality. And the speed of light still sets the limit on how fast information, real, usable information, can travel. So where does this leave us? We started with a simple observation. When you look at the stars, you're seeing the past. Light is fast, but the cosmos is vast, and even the fastest thing in the universe takes time to cross those distances. But as we've explored, that delay is more than just a quirk of astronomy. It's fundamental. The speed of light isn't really about light. It's about the structure of spacetime, about the maximum rate at which cause can affect effect, about the boundary between past, present, and future. Light happens to travel at this speed because light is massless, is less than #0. 5 is greater than, but the speed itself, c. 299,792,458 meters per second, is woven into the fabric of reality. It sets the exchange rate between space and time. It determines how motion affects the passage of time. It defines what events can influence each other. It creates the delayed universe you live in, where everything you see has already happened, and the present moment is observer-dependent. This isn't a limitation. It's the framework that makes a causally consistent universe possible. Without light's finite speed, cause and effect would lose their order. Time travel paradoxes would emerge. Reality would collapse into logical chaos. The speed of light prevents this. It's the universe's way of maintaining coherence, of ensuring that events unfold in a meaningful sequence, of protecting causality itself. And this protection comes at a cost. The cost is separation. Spatial separation becomes temporal separation. You and a distant star exist in the same moment, yet you cannot see each other's present. You can only see each other's past. The farther apart you are, the farther into the past you must look. This creates a kind of cosmic loneliness, a sense that the universe is not just vast, but temporally isolated. But it also creates something beautiful. Every photon is a messenger, a traveler that left its source in the distant past and crossed the emptiness to reach you. When you see starlight, you're receiving a message sent long ago, not a message with words or meaning, but a message nonetheless. This star existed, it burned, it sent light into the void. And against all odds, across vast distances, across vast times, that light found you. There's a patience to this. Light doesn't hurry, it travels at exactly c. Always. It crosses galaxies over billions of years, never speeding up, never slowing down. From the photon's own perspective, the journey is instantaneous. But from your perspective, It's an epic voyage across time and space. And when that photon finally enters your eye, its journey ends. Emission and absorption, billions of years apart from your perspective, yet simultaneous from the photons. 2 moments, 1 instant. This is the paradox of light. It connects distant events across time, yet experiences no time itself. It's the fastest thing in the universe, yet from its own frame, it doesn't move through time at all. And this brings us back to the present moment. Your present. The moment you're experiencing right now. This moment is shaped by light's speed. Everything you see is delayed by light's travel time. Everything you experience is a reconstruction of events that already happened. The sun you see is 8 minutes old. The person across from you is nanoseconds old. Even your own hand, held in front of your face, is a few nanoseconds in the past by the time the light from it reaches your eye. You have never seen the present. You have only ever seen the past. But here's the subtle comfort in this. The past you see is the only present you could see. The delay isn't a gap between you and reality. The delay is reality. It's the structure that makes cause and effect coherent. That prevents paradoxes. That allows time to have meaning. Without the delay, there would be no ordered sequence of events. No past leading to present, leading to future. Just chaos. The delayed universe is the only universe that can exist. But there's another layer to this. One that Einstein himself discovered 10 years after special relativity. It's called general relativity, and it shows that light's speed does something even stranger. It bends. Not the speed itself that remains constant, but the path light takes through space curves in the presence of mass and energy. This happens because mass and energy curve spacetime itself. In special relativity, spacetime is flat, like a smooth sheet stretched taut. In general relativity, mass creates dips and curves in that sheet, and light, traveling through curved spacetime, follows curved paths. These paths are called geodesics, the straightest possible paths through curved space. From light's perspective, it's traveling in a straight line, but from an outside perspective, the line is curved. The first confirmation of this came in 1919. During a total solar eclipse, astronomers measured the positions of stars near the sun's edge. Light from those stars had to pass close to the sun to reach Earth. Einstein's equations predicted the sun's mass would curve spacetime, bending the light's path and making the stars appear slightly displaced from their true positions. The amount of deflection was tiny, less than 2 arcseconds. But it was measurable. And when the measurements were made, they matched Einstein's prediction almost perfectly. Light had been bent by gravity, or more accurately, light had followed a straight path through curved spacetime. The distinction matters. Gravity isn't a force pulling on light. It's the curvature of the space through which light travels. This curvature affects more than just light's path. It also affects light's speed locally. In empty space, far from any mass, light travels at c, always. But near a massive object, spacetime is curved, and something subtle happens. From a distant observer's perspective, light passing near the mass appears to slow down. Not because the light itself is moving slower through space, but because time itself is passing more slowly near the mass. This is gravitational time dilation, again the same effect that causes GPS satellites' clocks to tick differently. Light still travels at c measured locally. If you were right there with the light, you'd measure it moving at exactly 299,792,458 meters per second. But from far away, looking at light passing through a gravitational field, it appears to take longer to cover the same distance. Not because light slowed down, but because time slowed down. This creates another kind of delay. Light, climbing out of a gravitational well, moving away from a massive object, appears redshifted. Its wavelength stretches, its energy decreases. This is called gravitational redshift. It's been measured countless times. Light from the surface of the Sun is slightly redshifted compared to light emitted in empty space. Light from white dwarfs, collapsed stars with intense gravity is even more redshifted. And light from near a black hole's event horizon is redshifted dramatically. If an object falls toward a black hole and emits light as it falls, that light becomes increasingly redshifted as the object approaches the event horizon. From a distant observer's perspective, the light takes longer and longer to escape. Time near the event horizon slows almost to a stop. The object appears to freeze, asymptotically approaching the horizon but never quite crossing it. This isn't an illusion. From the distant observer's frame, it really does take infinite time for the object to cross the horizon. From the object's own frame, it crosses quickly in seconds or minutes, depending on the black hole's mass. Both perspectives are correct. Time is genuinely relative. Black holes push this to an extreme. At the event horizon, the boundary beyond which nothing can escape spacetime is so curved that all future paths lead inward. Even light. Even massless photons, travelling at c, cannot escape. Not because they're moving too slowly, but because space itself is falling inward faster than light can move outward. Inside the event horizon, outward ceases to be a direction that leads away from the singularity. All paths forward in time lead to the centre. This is what makes a black hole black. Light cannot escape to tell distant observers what's inside. The interior is causally disconnected from the exterior. Information cannot cross the boundary in the outward direction, only inward. This creates another kind of horizon. The event horizon of a black hole is a one-way boundary in spacetime. Not a physical surface, not a wall, just a boundary beyond which light cones tip entirely inward. Cross that boundary, and your future light cone no longer includes any point outside. You cannot send signals out. You cannot influence external events. You are cut off from the rest of the universe. And yet, from your own perspective, nothing dramatic happens at the moment you cross. If the black hole is large enough, tidal forces are mild at the horizon. You pass through smoothly. Only later, as you fall toward the singularity, do things become catastrophic. But by then, it's far too late to escape. The speed of light, which defines causality everywhere else, defines the event horizon here. It's the boundary where space-time curvature becomes so extreme that even light cannot fight its way out. General relativity also predicts gravitational waves. When massive objects accelerate like two black holes orbiting each other, they create ripples in space-time itself. These ripples propagate outward at the speed of light. Not because they're made of light, but because they're disturbances in spacetime, and spacetime disturbances travel at c. In 2015, the LIGO observatories detected gravitational waves for the first time. Two black holes, each about 30 times the mass of the Sun, had spiraled into each other over 1 billion light-years away. The final moments of their merger released more energy than all the stars in the observable universe combined for a brief instant. That energy was released as gravitational waves. The waves travelled outward at the speed of light for over 1 billion years. By the time they reached Earth, they had weakened enormously. But LIGO's instruments were sensitive enough to detect them a distortion of spacetime smaller than the width of a proton. The waves passed through Earth, stretching and squeezing space itself by infinitesimal amounts. For a fraction of a second, the detectors recorded the ripples, and then the waves moved on, continuing their journey through the cosmos. This detection confirmed what Einstein had predicted a century earlier. Spacetime is not a static stage. It's dynamic, flexible, capable of carrying waves. And those waves travel at the speed of light because c is not just the speed of photons. It's the speed of causality, the speed at which any influence, electromagnetic, gravitational, or otherwise, can propagate through the universe. This universality is remarkable. Different forces, different carriers, same maximum speed. It suggests something deep about the structure of spacetime, something more fundamental than any particular force or particle. And this brings us to a question that lingers. Why this speed? Why 299,792,458 meters per second and not some other value? The honest answer is, we don't know. The speed of light is a fundamental constant. We measure it, we use it in equations, we build technology around it. But we can't derive it from anything more fundamental. It's just part of how this universe is. In some hypothetical other universe, c might have a different value, or perhaps no such speed limit would exist at all. But in this universe, c has the value it has, and that value shapes everything. It sets the scale of spacetime. It determines how fast information can travel. It creates the delayed universe. It enforces causality. Change c, and you'd change the entire character of physical law. Atoms might not form, stars might not burn, life might not arise. The universe would be unrecognizable, or it might not exist at all. This is sometimes framed as a fine-tuning problem. Why are the fundamental constants, the speed of light, the strength of gravity, the mass of the electron, set to values that allow complexity, structure, life? Some argue this points to design, others to a multiverse, where different universes have different constants, and we simply find ourselves in one where the constants permit our existence. Physics doesn't answer this question. It can describe how the universe behaves given the constants. It cannot explain why the constants have the values they do. That remains a mystery, one that may never be fully resolved. But what physics does make clear is this. The speed of light is not arbitrary. It's not a detail that could be tweaked without consequence. It's woven into the very fabric of spacetime, into the relationship between cause and effect, into the structure of past, present, and future. It's one of the load-bearing constants of reality. Change it, and the entire edifice changes. So when you look at the stars and see the past, you're not just observing a quirk of astronomy. You're seeing the fundamental architecture of the universe on display. The delayed universe is the signature of light's finite speed, and light's finite speed is the signature of spacetime's structure. It all connects. Distance and time, cause and effect, mass and energy. Light weaves through all of it, revealing the deeper patterns. And perhaps that's the quiet gift of understanding light's speed. Not that it answers every question, but that it shows how questions connect. How a single constant c ripples through physics, shaping time, space, gravity, causality. How the universe is not a collection of separate phenomena, but a unified whole. And how even in strangeness, time dilation, length contraction, the relativity of simultaneity, there's a deeper consistency, a logic that holds, a structure that remains reliable. This is worth sitting with for a moment. The universe is stranger than everyday intuition suggests. Time is not absolute, space is not fixed, simultaneity is relative. Light from a distant star is ancient by the time it reaches you. Your present moment is not the same as someone else's present moment. Clocks moving at different speeds tick at different rates. Mass curves spacetime. Gravity bends light. All of this is real, measured, confirmed. Not speculation, not philosophy. Physics. And yet, despite all this strangeness, the universe remains coherent. Equations still work. Predictions still hold. Clocks still tick, even if they tick at different rates. Cause still precedes effect, even if the order depends on reference frame. Light still travels at sea, always. The universe does not require human intuition to function. It operates according to its own logic, and that logic, once understood, is consistent. This consistency is the deeper comfort. Not that everything is simple, but that complexity does not mean chaos. Relativity is counterintuitive, but it's not arbitrary. It follows from accepting one fact: light's speed is constant and working through the consequences logically. The consequences are strange, but they fit together. They form a coherent picture. And that coherence is reassuring. It suggests the universe is knowable, even if it's not always intuitive. Mystery remains, of course. We don't know why C has the value it does. We don't know what happens at the singularity inside a black hole. We don't fully understand how quantum mechanics and general relativity fit together. But these are productive mysteries, questions that drive research, experiments, discovery. Not gaps that undermine understanding, but frontiers that invite exploration. And in the meantime, what we do understand holds firm. Light travels at sea, time dilates with motion, mass curves spacetime. These are not tentative ideas waiting to be overturned. They're confirmed facts, tested thousands of times, woven into the technology you use daily. The universe is reliable, even when it's strange. And this strangeness has a human dimension worth considering. Because you live in this delayed universe every moment of your life. Not just when you look at stars. Every moment. Right now, as you read or listen to these words, you're experiencing delays. Tiny ones, imperceptible in isolation. But real nonetheless. Light from the screen or page takes a few nanoseconds to reach your eyes. Then your brain takes additional time, tens of milliseconds, to process that light into a conscious perception. By the time you're aware of seeing something, the moment has already passed. You've never seen anything in real time. Your entire experience of the present is slightly delayed, constructed from information that's already old by the time it reaches your consciousness. This is true for all perception. Sound travels slower than light, about 343 meters per second in air. When you watch someone speak from across a room, you see their lips move before you hear the words. The delay is small, a few milliseconds for every meter of distance. Your brain usually compensates, synchronizing sight and sound so the experience feels unified. But the delay is there. Thunder and lightning provide a more noticeable example. You see the flash instantly well, with the light travel delay, but that's imperceptible at typical storm distances. Then you wait. 5 seconds per mile, roughly. The sound is traveling toward you at the speed of sound, far slower than the light that revealed the flash. The event, the lightning strike, is singular, but your perception of it is split across time. Light arrives first, sound follows. Both carry information about the same event, but they arrive at different times because they travel at different speeds. Even touch has a delay. When you touch something, pressure sensors in your skin generate electrical signals that travel along nerves to your brain. Those signals move at speeds ranging from about 1 meter per second to over 100 meters per second, depending on the type of nerve fiber. Slower than sound. Much slower than light. So there's a delay between contact and perception. Touch a hot surface, and the pain signal takes time to reach your brain. By the time you feel it and react, you've already been burned. The delay is brief, tens to hundreds of milliseconds. But it's there. And it's unavoidable. Information, whether electromagnetic, acoustic, or biochemical, takes time to travel. Your brain compensates remarkably well. It synchronizes inputs from different senses. It predicts where moving objects will be by the time you react to them. It constructs a coherent experience of now from information that arrives at different times. This construction is seamless most of the time. You don't notice the delays. You experience the world as immediate, present, unified. But beneath that seamless experience, there's a constant process of temporal adjustment. Your brain is solving the delay problem continuously. This raises a philosophical question. If you've never experienced the true present, if all perception is delayed, what does now even mean? One answer is that now is the moment you're conscious of. It doesn't matter that the light entering your eye left its source nanoseconds ago. What matters is that your consciousness assembles those inputs into a unified experience. That experience is your present. Another answer is that now is fundamentally observer-dependent. Your now includes the events that are simultaneous in your reference frame. Someone else's now includes a different set of events. There's no universal present moment, no single now that everyone shares. And yet, this doesn't make experience less real. Your present moment is real for you. It's the only present you can experience. The delay doesn't diminish it. It's simply the structure within which experience happens. This connects back to the stars. When you look up at night and see Betelgeuse, that light is 650 years old. But from your perspective, Betelgeuse exists in your present. You see it now. The fact that the light is ancient doesn't make the experience less immediate. It just means the present has depth. Temporal depth. Your field of view contains events from different moments in time. The moon, about a second old. The sun, 8 minutes old. Proxima Centauri, over 4 years old. Each light source contributes to your present experience, yet each carries information from a different moment in the past. The present is not a single instant. It's a collection of pasts arriving now. And this delayed universe creates a kind of connection across time. Every photon is a link, a bridge between the moment it was emitted and the moment it's absorbed. When you see a star, you're connected to that star's past, not by being there, but by receiving light that was there. The photon carries information, energy, wavelength, polarization that tells you something about conditions at the source. How hot the star was, what elements it contained, how fast it was moving. That information has traveled across space and time to reach you, and in receiving it, you learn about a place and time far removed from here and now. This is why astronomy is inherently historical. Looking outward in space means looking backward in time. You can never see the distant universe as it is, only as it was. And the farther you look, the deeper into history you peer. This isn't a limitation of telescopes. It's a consequence of light's finite speed. No technology can overcome it. The delayed universe is the only universe we can observe. But there's a subtle beauty in this, because it means the universe is continuously revealing its history. Every moment, light from farther away arrives for the first time. The cosmic microwave background, the oldest light we can see, is still arriving. New photons from that ancient event reach Earth every second. The history of the universe is not locked away. It's unfolding, arriving, present in the light that reaches us. You can look up and see billions of years of cosmic evolution laid out in the sky. not as a static picture, but as a dynamic process still delivering its messages. And those messages change our understanding. By observing distant galaxies, astronomers discovered the universe is expanding. By measuring how that expansion has changed over time, they discovered dark energy. By looking at the cosmic microwave background, they learnt about the universe's composition, age, and early conditions. All from light, ancient light, traveling at sea, carrying information across billions of years. The speed of light creates the delay, but the delay creates the record. Without it, the past would be inaccessible. You could only see the present, a narrow, infinitesimal slice of time. But because light takes time to travel, the past is always arriving. History is embedded in the light around you. This is true even for relatively nearby objects. When the sun goes through its 1-1-year activity cycle, we observe changes in solar output, flares, sunspot numbers, that those observations are always 8 minutes behind. We see the sun as it was 8 minutes ago. By the time a solar flare's light reaches Earth, the flare itself has already evolved or dissipated. This delay becomes significant for space weather forecasting. A solar flare can release charged particles that take hours or days to reach Earth, potentially disrupting satellites, power grids, and communications. Scientists watch for flares using light-speed observations, then model how the slower-moving particles will travel. The 8-minute delay in seeing the flare is actually helpful. It provides warning time, but it also means the data is historical the moment it's received. The sun's current state is always unknown. What we see is what it was doing 8 minutes ago. For Mars missions, the delay is operational. Commands sent to rovers take anywhere from 3 to 22 minutes to arrive, depending on the planet's positions. Replies take the same amount of time to return. Round-trip communication can take over 40 minutes. This makes real-time control impossible. Instead, rovers are programmed with autonomous capabilities. They can navigate obstacles, select targets, adjust instruments, all without waiting for human input. Engineers send general instructions, then wait. The rover executes, sends back results. Minutes or hours later, those results arrive on Earth. The delay shapes mission design. It determines what's possible, not as a technical hurdle to overcome, but as a fundamental constraint written into spacetime. Even future interstellar missions will face this. If humanity ever sends a probe to Proxima Centauri, 4.24 light-years away, communication will take over 4 years each way. Send a signal to the probe, 4 years to arrive. Probe replies, 4 years back. 8 years round trip. By the time you receive a status update, it describes conditions from 4 years ago. Any problem the probe encountered would be long resolved or long catastrophic before Earth even knows it happened. Autonomy would be essential, but so would patience. Patience with delay. Acceptance that real-time connection is impossible across those distances. The delayed universe limits what can be coordinated, but it doesn't prevent exploration. It just shapes how exploration must happen. And in a way, this makes exploration more profound. Because sending a probe 4 light-years away means sending it into a future you'll never see in real time. You can only receive its past. The probe exists in the present, navigating Proxima's system, recording data, making decisions. But from Earth's perspective, it's always 4 years behind. There's a kind of loneliness in that, a separation not just of space, but of time. And yet, the connection persists. Light carries information across the void. Slowly, patiently, but reliably. The speed of light is finite, but it never fails. Photons always travel at sea, always. They don't get tired, Don't slow down. Don't forget their message. They just travel, for as long as it takes. So let's return one last time to the question we started with. Why does looking at the stars mean looking at the past? The simple answer: because light travels at a finite speed, and space is vast. That the deeper answer is more subtle. Because the universe has a maximum rate at which cause can affect effect, a speed limit on information, influence, causality itself. Light happens to reveal this limit because light is massless. Massless things travel at the maximum speed, and that maximum speed is c. The speed of light isn't about light. It's about the geometry of spacetime, about how space and time are woven together, about the exchange rate between distance and duration, about the boundaries of causality. This speed creates the delayed universe, not as a bug, but as a feature, not as something to overcome, but as the structure that makes reality coherent. Without this delay, cause and effect would lose their order. Events could influence their own past. Paradoxes would emerge. The universe would collapse into logical chaos. The speed of light prevents this. It creates a buffer, a region of space-time where events can unfold independently before their influences reach each other. This buffer is what allows the present moment to exist, not as a universal instant, but as a local experience, observer-dependent, reference frame specific, but real nonetheless. And this is where the delayed universe becomes comforting rather than alienating. Yes, everything you see is in the past. Yes, simultaneity is relative. Yes, time passes differently for different observers. But all of this emerges from a single, simple, unchanging constant. C. 299,792,458 meters per second. The same everywhere. The same always. That constancy is what makes relativity work. What makes the equations balance. What makes the universe predictable. Light speed never changes. It doesn't care about your motion. It doesn't depend on the source. It's just c. Reliable, absolute. And from that one absolute, all the relativity follows. Time dilation, length, contraction, the equivalence of mass and energy, the relativity of simultaneity, the structure of causality. All of it stems from accepting that light speed is constant and working through the consequences honestly. This is what physics does. It doesn't tell you what you want to hear. It tells you what measurements show. And if those measurements challenge intuition, physics adjusts the framework, not by abandoning logic, but by following logic wherever it leads. Einstein didn't invent time dilation because it seemed elegant. He derived it because it was the only way to reconcile constant light speed with consistent physics. The equations demanded it. Experiments confirmed it. And now it's woven into technology, into astronomy, into the way we understand reality. This is science at its best. Following evidence, building models that match observation, refining understanding when new data arrives, not claiming certainty where none exists, but also not shying away from conclusions when evidence is clear. And the evidence is clear. Light speed is constant. Time is relative. Space is relative. Mass and energy are equivalent. Space-time can curve. Gravity propagates at light speed. These aren't speculations. They're confirmed facts. Tested. Measured. Used. Your GPS depends on them. Particle accelerators demonstrate them. Gravitational wave detectors confirm them. The delayed universe is the real universe, the only universe there is. But understanding this doesn't diminish wonder. If anything, it deepens it. Because the universe could have been arbitrary. It could have been chaos. Instead, it's governed by laws, regularities, patterns, constants. And those laws fit together. Electromagnetism connects to relativity. Relativity connects to gravity. The speed of light appears in equations about energy, about space-time curvature, about quantum fields. It's not isolated. It's woven through everything. This interconnectedness is profound. It suggests the universe is not a collection of separate phenomena, but a unified whole. Different aspects of one reality, different views of the same underlying structure. And that structure, while counterintuitive, is reliable. You can trust it, not because it matches human expectations, but because it's consistent with itself. The universe plays by rules. Strange rules, perhaps, but rules nonetheless. And those rules don't change. Light always travels at sea. Cause always precedes effect. Energy is always conserved. These principles hold. They've held for billions of years. They'll hold for billions more. The universe is stable, even when it's strange. And perhaps that's the quiet comfort here. Not that everything makes immediate sense, but that there is sense to be made. Not that intuition always succeeds, but that careful reasoning does. The delayed universe felt like a problem at first. How can you see the past when you look at stars? How can light speed be constant for all observers? But follow the logic. Work through the mathematics. Test the predictions. And what emerges is not confusion, but clarity. Not chaos, but structure. A universe where space-time has geometry, where causality has limits, where time and space are aspects of a deeper unity. The strangeness doesn't go away, but it becomes coherent strangeness, understandable strangeness, the kind that deepens appreciation rather than undermining it. Because now, when you look at the stars, you see more than distant lights. You see photons that have been traveling for years, centuries, billions of years. Each one a messenger from the past, each one carrying information across the void at exactly c. Never faster, never slower. Just this one speed, woven into the fabric of everything. And you see the structure of space-time itself. The way light cones define what can influence what. The way time dilation stretches moments. The way distant galaxies show you the universe's history. Not because someone arranged it that way, but because this is how space-time works. This is the universe you live in. The delayed universe. The only universe that can exist while maintaining causality. And in that understanding there's a kind of peace. Not the peace of having all questions answered, but the peace of knowing the questions make sense. Of knowing the universe is knowable. Even when it refuses to match intuition. Even when it demands careful thought. The universe is patient with us. It doesn't change its laws to accommodate human preferences, but it also doesn't hide them. The laws are there, written in the behavior of light, in the motion of particles, in the expansion of space. Available to anyone willing to observe carefully, to measure precisely, to think honestly. And that availability is a gift, because it means understanding is possible. Not complete understanding, there will always be deeper questions, but genuine understanding. The kind that reveals structure, the kind that makes predictions, the kind that works. Relativity works. GPS proves it daily. Particle accelerators demonstrate it constantly. Gravitational wave observatories confirm it repeatedly. The delayed universe isn't a theory waiting to be replaced. It's a description of how things are. Confirmed, tested, reliable. So when you look at the stars tonight, if you do, remember, you're seeing ancient light. Light that left its source long before you were born. Maybe before humanity existed. That light has been travelling at exactly 299,792,458 meters per second, never speeding up, never slowing down, crossing the vast emptiness between there and here, between then and now. And when it finally enters your eye, it completes a journey that, from the photon's own perspective, happened instantaneously. Emission and absorption. One moment. But from your perspective, an epic voyage across time and space. Billions of years compressed into a single point of light. This is the delayed universe. Strange, beautiful, coherent. And it's the only universe that could exist. Because the speed of light is not just a speed, it's the structure of reality itself. But before we close, there's one more layer worth exploring. The relationship between light speed and the scale of the universe. Because these two things are intimately connected, the universe is approximately 13.8 billion years old. Light travelling at sea for 13.8 billion years covers a specific distance, about 13.8 billion light-years. This defines the edge of the observable universe, not in space, but in time. You can't see farther back than the beginning, and light hasn't had time to reach you from beyond a certain distance. So the observable universe has a horizon, a boundary set by light's speed and the universe's age. Beyond that horizon there might be more universe. In fact, there almost certainly is. But you can't see it. Light from those regions hasn't had time to reach you yet. The delay is too long, longer than the universe has existed. This creates a humbling perspective. Everything you can observe, every star, every galaxy, every photon, lies within a sphere whose radius is determined by c, multiplied by the age of the universe. That sphere is enormous, billions of light years across, containing hundreds of billions of galaxies. But it's also fundamentally limited, not by technology, by the laws of physics. You cannot see beyond the observable horizon because light from beyond it has not arrived yet. And if the universe's expansion continues accelerating, which current observations suggest it will, some regions will recede faster than light can travel toward you. Light from those regions will never reach you. Ever. There are parts of the universe you are cosmologically separated from, not by distance alone, but by the combination of distance and expansion. Those regions exist. They're real, but they're beyond the reach of your light cone. Forever. This might sound isolating. And in a sense, it is. The universe is vast beyond comprehension, and most of it is hidden from view. But there's another way to think about it. The observable universe is still unfathomably large, still filled with billions of galaxies, still revealing new structures, new phenomena, new mysteries, every time we look more carefully. And all of that is accessible. Not immediately, not in real time, but accessible through light. Patient, constant light, traveling at sea, carrying information across the cosmos, delivering messages from the deep past, showing us how galaxies formed, how stars ignited, how the universe evolved. The delayed universe is also a recorded universe. A universe where history is embedded in the light around you. And that history tells a story. The cosmic microwave background, that faint glow from 380,000 years after the Big Bang, shows the universe when it was hot, dense, nearly uniform. Tiny fluctuations in temperature, just a few parts in 100,000, hint at the seeds of future galaxies. Look at galaxies a billion years later, and you see those seeds have grown. Gravity has amplified the initial fluctuations. Gas has collapsed. Stars have formed. Look farther forward in time, closer to the present, and you see galaxies colliding, merging, evolving. Stars going supernova. Black holes growing. The universe becoming more complex. All of this is visible because light from each epoch is still arriving. The universe's history is not hidden. It's spread across the sky, laid out in layers of light. The farther you look, the farther back you see, and if you look carefully, you can trace the evolution. This is one of the most remarkable achievements of modern astronomy. By measuring light from different distances, different times, astronomers have reconstructed the universe's history. Not perfectly, not completely, but with remarkable detail. They know when the first stars formed, when galaxies began to cluster, when the universe's expansion started accelerating. All from light, photons that travelled for billions of years, carrying information about their sources. The speed of light made this possible, not despite being finite, but because it's finite. If light travelled infinitely fast, you'd see everything in its present state. No history, no record. Just now. But light's finite speed creates a cosmic archive. Every distance corresponds to a time. Every observation is a glimpse into the past. And together, those glimpses reveal how the universe has changed over billions of years. There's a meditative quality to this realization. The universe is not static. It's evolving, growing, changing. But that change happens slowly, on timescales that dwarf human lifetimes, on timescales that dwarf civilizations. A galaxy that appears fixed in the night sky is actually moving, rotating, evolving, but so slowly that it looks the same from one human lifetime to the next. Stars that seem eternal are burning fuel. They're moving through cycles of fusion. Someday they'll exhaust their fuel and transform into white dwarfs, neutron stars, black holes. But someday is millions or billions of years away. The universe has patience. It doesn't hurry. It unfolds according to the laws of physics. Slowly, inevitably. And light carries the record of that unfolding at exactly c. Never faster, never slower. Just this one speed, connecting every moment in the universe's history to every observer willing to look. And this connects back to human experience. Because you, too, are part of this slow unfolding. You're made of elements forged in stars. Carbon, oxygen, nitrogen, iron. All created in stellar cores over billions of years. Released into space when those stars exploded. Incorporated into new clouds of gas. Collapsing into new stars, new planets. Eventually, Earth. And eventually, you. The atoms in your body are ancient, billions of years old, forged in stars that no longer exist. You're made of stardust, not metaphorically, literally. And the light reaching your eyes right now from the sun, from distant stars, was emitted by fusion reactions, similar to the ones that created those atoms. You're connected to the cosmos, not by mysticism, but by physics. By the processes that govern stars, light, matter, time. By the laws that shape the delayed universe. And those laws are not oppressive. They're not restrictions that diminish existence. They're the framework that makes existence possible. Without the speed of light setting a limit on causality, the universe would be incoherent. Without time dilation and length contraction balancing light's constant speed, physics would contradict itself. Without the delayed universe, there would be no cosmic history to observe, no record of where we came from, no light from distant galaxies to show us the universe's evolution. The limitations are also enablers. They create structure. They allow complexity. They make the universe comprehensible. And comprehensibility is a gift, because it means you can understand. Not everything there will always be deeper questions, but enough to see the patterns, enough to appreciate the structure, enough to recognize that the universe, for all its strangeness, is not random. It's governed by laws, and those laws are beautiful. Not in the aesthetic sense, though the mathematics can be elegant, but in the deeper sense. Beautiful because they're consistent, because they connect disparate phenomena, because they reveal unity beneath apparent diversity. The speed of light is the same whether you measure it on Earth or in a distant galaxy, whether you measure it today or 1 billion years ago. That constancy is profound. It suggests the universe has integrity, that it's not capricious, that the rules don't change arbitrarily, and that you can trust those rules. You can build on them. You can predict from them. You can navigate reality using them. This is what science offers. Not certainty about every detail, but confidence in the framework. Confidence that the universe is knowable. That careful observation reveals truth. That patterns exist and can be understood. And the speed of light is one of those patterns. Constant, reliable, fundamental. It shapes time. It shapes space. It shapes causality. It creates the delayed universe. And in doing so, it creates the possibility of understanding. Because if light's speed were infinite, you couldn't learn the universe's history. You'd only see the present, a single moment, divorced from context. But light's finite speed means the past is always arriving. History is embedded in every photon. And by studying those photons, where they came from, when they were emitted, what they've traveled through, you can reconstruct the story, the universe's story, and your story as part of it. This is the delayed universe. Not a flaw, not a limitation, a feature. The feature that makes the cosmos knowable, that preserves history, that protects causality, and that allows you here, now, to look at ancient light and understand what it means. This is the quiet gift of science. It doesn't take the mystery away. It teaches you how to live comfortably inside it, how to appreciate strangeness without demanding it conform to intuition, how to find reliability within complexity, how to see that the universe, while vast and often counterintuitive, is not chaotic. It has structure, laws, patterns, and those patterns hold. They've held for billions of years. They'll hold for billions more. Light will continue traveling at sea. Time will continue being relative. Cause will continue preceding effect. The universe will continue being strange, and coherent, and knowable. So when you look at the stars and see the past, remember, this is the only way the universe could work. The delayed universe is not a compromise. It's the solution. The way reality maintains consistency. The way causality stays protected. The way the past connects to the present. And the speed of light c, 299,792,458 meters per second, is the thread that weaves it all together. Constant, reliable, fundamental, always the same. Everywhere. Forever. This is the delayed universe. Strange, beautiful, coherent. And it's the only universe that could exist, because the speed of light is not just a speed, it's the structure of reality itself. There's one more thought worth holding before we rest, about the relationship between knowledge and comfort. Sometimes, learning how the universe works can feel destabilizing. Finding out that time is relative challenges the sense that moments are shared. Discovering that simultaneity depends on reference frame unsettles the idea of a universal now. Realizing that everything you see is already in the past might create a sense of disconnection, as if the present is always out of reach. But there's another way to hold these truths, not as losses, but as deeper understanding. The universe doesn't owe you intuitive answers. It doesn't have to match the expectations evolution gave you. Your intuition was shaped by moving at low speeds, experiencing weak gravitational fields, interacting with objects at human scales. It's perfectly tuned for that domain, but the universe is larger than that domain. It includes extreme speeds, intense gravity, vast distances, tiny quantum scales. At those extremes, intuition reaches its limits. Not because intuition is broken, but because it was never designed for those conditions. Recognizing this removes the pressure. You don't have to intuitively grasp time dilation. You just have to accept that it's real. Confirmed by measurement, woven into technology, consistent with equations. Real. And once you accept that, the strangeness becomes less threatening. It's just how things are at scales beyond everyday experience. The delayed universe is one of those things. It feels strange because you're never aware of the delay in daily life. The nanoseconds it takes light to cross a room are imperceptible. So your brain treats vision as instant, and for practical purposes, it is. But scale up to astronomical distances, and the delay becomes impossible to ignore. Suddenly, the principle you could overlook becomes the dominant feature. And that can feel disorienting, like discovering that something you thought was solid is actually mostly empty space. Which, by the way, is also true. Atoms are mostly empty space. The nucleus is tiny compared to the electron cloud. But the electromagnetic forces between atoms create the sensation of solidity, so tables feel solid even though they're mostly void. The same principle applies here. The delayed universe feels immediate even though it's fundamentally delayed. Your brain bridges the gap. And for everyday purposes, that's fine. The delays don't matter. But knowing they're there deepens understanding. It reveals the underlying structure, the way things actually work, beneath the seamless experience. And there's comfort in that structure. Because structure means predictability. It means the universe isn't arbitrary. Light always travels at c. Time dilation always follows the same equation. Length contraction always pairs with time dilation in just the right way to keep light speed constant. These aren't random coincidences. They're consequences of spacetime's geometry. And that geometry is consistent. Everywhere, always. The universe has rules. And those rules don't change depending on whether you're watching. They just are. This is reliability at a deep level. Not the reliability of familiar experience, but the reliability of fundamental law. And perhaps that's the ultimate comfort. Not that everything is simple, but that everything is lawful. Not that you can intuitively grasp every principle, but that those principles exist and can be understood. The universe is strange, but it's not chaotic. It's complex. But it's not random. And it's knowable. Not completely, there will always be deeper questions. But genuinely, in ways that make predictions, in ways that build technology, in ways that reveal history. The speed of light is one thread in that tapestry, but pulling on that thread reveals so much. Time's relativity, space's flexibility, causality's limits, the structure of spacetime, the equivalence of mass and energy, the delayed universe, the cosmic horizon, all from one constant, c. 299,792,458 meters per second. The same everywhere. The same always. And in that constancy, there's something to hold on to. Not as an anchor against change, the universe does change, but as a reminder that beneath the change, there's structure. Beneath the complexity, there's order. Beneath the strangeness, there's coherence. So rest in this. The universe is vast. It's ancient. It's strange beyond everyday intuition. But it's also reliable, governed by laws that hold across billions of light years and billions of years. Light travels at sea, always. And that constancy creates the delayed universe, the only universe that can exist while maintaining causality. The only universe where past, present, and future have meaningful structure. The only universe where history is preserved in light. Where you can look at ancient stars and see the cosmos as it was. Where every photon is a messenger from the past, travelling at exactly c. Patient, constant, reliable, for as long as it takes. This is the delayed universe. Strange, beautiful, coherent. And it's the only universe that could exist. Because the speed of light is not just a speed, it's the structure of reality itself. Better sleep, a lighter day.